Hello and welcome to the remediation video that we'll be doing for balancing equations and stoichiometry. As you saw in the invitation letter, there are actually 4 topics that we will be covering during this video. If you have not already done so, you'll need to be taking notes over this video in order to get into the remediation session. So if you haven't already got note-taking materials, you'll need to do that. And then also remember that in order to get into the remediation session, not only will you need the video notes, but you will also need the homework assignment that is posted on our website. Don't forget to check your answers and get questions answered if you need. So during this remediation video, we'll first of all be talking about how to balance equations. You'll notice that these questions were referenced in multiple choice, questions 26 through 45. We'll then talk about how to find mass by subtraction. We've been doing this throughout the year in the lab setting, and we used this as the opportunity to make sure that you knew how to do this. If you didn't, we'll be covering that in just a moment. Then wrapping up the video, we will be talking about mass problems. We'll talk about how to solve them, but then we'll also find out that mass problems are a step along the way to figuring out percent yield, which is where we will wrap up today's video. So first of all, talking about balancing equations. The idea with balancing equations is that we understand that chemical equations represent chemical reactions. We also understand that the law of conservation of mass says that we cannot create or destroy matter, which means everything that goes into a reaction, which we call the reactants, has to also come out of the reaction, and we call these the products. And so the problem is that many times when we write these equations that represent reactions, many times they are not balanced when we first write them down. For example, if we look at this equation, you may remember this is actually the equation that represents the burning of propane. Propane, C3H8, when it combusts, reacts with oxygen, and that then produces carbon dioxide and water. Now, we look at this, and it may seem abstract. What exactly do these molecules look like? Well, if we look at them in picture form, we find out that a C3H8 molecule is literally 3 carbons in gray surrounded by 8 hydrogens in blue. Then oxygen is O2. It would be important for you to remember at this point that we have 7 different elements, which are what we call diatomics, meaning that we will never see them alone. They group together in groups of 2. These include iodine, bromine, chlorine, fluorine, oxygen, nitrogen, and hydrogen. And if you find these elements on your periodic table, you'll notice that they start at iodine, go up to fluorine, go left to nitrogen, and then jump over to hydrogen. We need to remember, though, that these elements, again, are never found by themselves, so you'll never see just oxygen, it's O2. Then carbon dioxide is 1 carbon bonded to 2 oxygens, and then finally water, of course, is H2O. You'll notice that even though oxygen is diatomic, in this case, because it's bonded to something else, hydrogen, it does not need to be O2 in order to figure this out. You balance charges. So the take home with the diatomics is they will only be bonded together in groups of 2 if they are by themselves. Otherwise, we figure out how many we need by balancing charges. Okay, so now that we've got a bit of a sense of this equation that we're trying to balance, what we do is we start on the left and work to the right. So if we start on the left, we see that we've got 3 carbons there on the left. Well, we've got a problem because we're putting in 3 carbons, but we're only getting out 1 carbon. And we can see this 1, 2, 3 carbons here, and we see that we only have 1 carbon on the right. Now, some would say then, well, why don't we just come along and why don't we attach 2 more carbon atoms to the CO2? And we can't do that because carbon and oxygen don't bond together in those ratios. So in order to fix the problem, instead of adding additional carbons to the product side, what we do is we place a coefficient in front of the carbon dioxide. The thought now being, we've got 3 carbons We've got 3 carbons on the left in the C3H8, and now by placing a 3 in front of the carbon dioxide, we've now got 3 carbons on the right side, the product side. Here's 1 and 2 and 3. So 3 carbon dioxides represents 3 carbons, and now our carbons balance. So now as we continue on, we see that we've got 8 hydrogen atoms. Now, our hydrogen atoms on the right side are tied up into the water, but you'll notice that each water molecule only contains 2 hydrogens. So if we want 8 hydrogen atoms on the right-hand side, we are going to need 4 water molecules, and we can see that by putting the 4 there, 4 times 2 is 8, but we can see 2, 4, 6, 8 water molecules, or I'm sorry, 8 hydrogen atoms tied up in these 4 water molecules. So now finally we need to balance the oxygens. Here on the left we've got oxygen in packages of 2. Here on the right we've got oxygens in both products. So in the carbon dioxide we've got 3 times 2, which is 6. 1, 2, 3, 4, 5, 6. And then 4 times 1, which is 4. 1, 2, 3, 4. So if we add up the 6 oxygens in CO2 and the 4 oxygens in water, that gives us a total of 10 oxygens. To get 10 oxygens on the left, of course, we then need 5 oxygen molecules, and now we have 2, 4, 6, 8, and 10 oxygen atoms on the left as well, and that balances. Now, it's helpful when we balance equations to be able to see these pictures, but as you know, we won't always have the pictures. So what we need to do is we need to become good at balancing these equations without actually seeing the drawings of the molecules. But the process is the same. We start on the left, we work to the right, and we make the atoms balance. Now along the way we talked about some helpful hints. So let's get started on this first one and see how we do. So starting on the left we've got 1 aluminum, and looking on the right we've also got 1 aluminum, so the aluminum's balance. You'll notice next we come to nitrogen. But we'll notice that nitrogen is actually a part of the polyatomic NO3. And because nitrogen is tied up in NO3, when we look on the right, we see that there are also NO3s on the right side, meaning that we don't have to balance the nitrogens, we can balance the NO3s. So looking on the left side, we see that there are 3 NO3s. Looking on the right side, we see that there's 1 NO3, which means we need a 3 in front of the NaNO3, and that gives us 3 NO3s. Now we balance the sodiums, and we see that on the left we have 1 Na, and on the right we now have 3 because of the 3 in front here, which then requires a 3 in front there. Now we look at the O, but we see that O is a part of OH, hydroxide, and OH is also present on the right, and conveniently you'll notice that we've got 3 OHs here and 3 OHs there, and that balances. So it balances with a 1, a 3, a 1, and a 3, and you'll notice that if it balances with a 1, we don't write the 1, we leave it blank because it's understood. Now looking at our second example, you'll see that we've got 1 potassium and 1 potassium, so that balances. Now again, here we have NO3. And so in the previous example, we were able to balance the NO3s rather than the nitrogens and the oxygens. But you'll notice in the second example, the NO3 does not stay together. It breaks apart and becomes NO2. As a result, we cannot balance the NO3s, we have to balance the nitrogens and the oxygens. So starting again, 1 potassium, 1 potassium, 1 nitrogen, 1 nitrogen. So we're doing great there. So now we're left with oxygens, and you'll notice that on the left we have 3 oxygens, and on the right we have 2 plus 2, which is of course 4. Now the problem is that we now have an odd number of elements, oxygen, on the left, and an even number on the right. And you may remember that we talked about the idea that this is what we call an odd-even conflict. This 3 on the left, being an odd number, needs to be turned into an even number so it'll balance the even number on the right. So in order to make that odd number even, we put a 2 out front, and then we start over. So now we have 2 potassiums, which means we need a 2 there. Now we've got 2 nitrogens, we now have 2 nitrogens there, and then you'll notice on the left we've got 6 oxygens, and then we've got 4 plus 2 is 6 oxygens, so that is also balanced. Now moving down to our next example. Here you'll notice that we've got 1 iron on the left, and we've got 2 irons on the right, so we simply put a 2 in front of the iron. Now looking at the hydrogens, we've got 2 on the left, we've got 2 on the right, so that's good. Now we run into sulfur, but again we notice that sulfur is a part of SO4, and in fact the SO4 stays together, so we can balance the SO4s. So on the left we have 1 SO4, and on the right we have 3, so we put a 3 in front of the H2SO4. But this creates a problem, because even though we've already balanced the hydrogens, you'll notice that the hydrogen is no longer balanced because of the 3. We now have 6 hydrogens here, which requires that we put a 3 there, and now our hydrogens are balanced as well. Now, one of the other hints that we talked about was the idea that you never want to balance oxygens first. Always save it for last. So when we look at our last example, you'll notice that oxygen is first. We're going to skip it. We're going to go on from there, and we've got 1 carbon, 1 carbon, we've got 2 sulfurs, and we've got 1 sulfur, so we'll place a 2 there. Now we can come back and do our oxygens, and you'll notice that on the right we've got 2 here, and we've got 4 there, for a total of 6, which means we need to put a 3 there, and that balances. Now, as you're working through these, and maybe as you're looking over the examples that we had on the test, one of the things that you may have noticed is that sometimes, even when we try all of our tricks, these things don't balance. They're not as simple as maybe we thought they might be. Remember, we always have the opportunity to try what we call trial and error. So if you find that you find an equation that you can't get to balance, try this. What you can do is actually just put, and I'll sort of use the first example as an example, put a 1 in front of the first substance, and then see if that makes the rest of everything balance by adding numbers in the other spaces as you need. If that doesn't make it balance, erase everything, put a 2 there, and keep going. And eventually you'll find fairly quickly that one of these will actually make these things balance. So those are the things that you need to be able to do relative to balancing equations. And so we're ready to start talking about what are called mass-mass problems. Mass-mass problems are problems that rely on what's called a stoichiometric ratio. Stoichiometric ratios are simply the coefficients from balanced equations. But what a mass-mass problem allows us to do is predict how much reactant or product will be consumed or created in a chemical reaction. To solve these, the first thing that we need is a balanced equation. Once we've written a balanced equation, the next 3 steps, which are the mathematical steps, are always the same. We'll take a mass and convert it to moles. We'll then apply the mole-to-mole ratio from the balanced equation, and then we'll convert moles to grams. You'll notice that these problems start with a mass and they end with a mass. That's why we call them mass-mass problems. If you'd like another second to write down these steps, feel free to pause the video. Otherwise, we're going to move forward and we're going to solve one of these problems. So, this is a typical mass-mass problem. It says, what mass of copper 2 nitrate will be consumed when 10.2 grams of sodium chloride is reacted with it? Now, you probably noticed that on the test, we gave you the balanced equation. And so when you were given this equation, it was balanced for you, and that will be the case in all of the remediation stuff as well. We will be giving you the balanced equations. So we know that we're taking copper nitrate, copper 2 nitrate, which is this guy here on the left. So we are taking copper 2 nitrate and reacting that with sodium chloride. And then our products are copper 2 chloride and sodium nitrate, and that balances with a 1 and a 2 and a 1 and a 2. So in order to solve this problem, the first thing that we need to do is figure out what we're solving for and where we're starting. So you'll notice that it says what mass of copper 2 nitrate will be consumed. That tells us that our X is copper 2 nitrate. Then we're given this other information that says 10.2 grams of sodium chloride reacts with it. These two bits of information then become our starting point and our goal. So we are going to start with the 10.2 grams of sodium chloride, and our goal will then be the mass of the substance that we are solving for, which in this case is the copper 2 nitrate. Now at this point, going back to the steps, this becomes a three-step dimensional analysis process. It's always grams to moles, then moles to moles, then moles to grams. So the first step is grams to moles. Sodium off the periodic table is 23.0 grams. Chlorine is 35.45, which rounds, 35.45, which rounds to 35.5. And we add that up and we find out that 58.5 grams of NaCl is 1 mole of NaCl. So now we've converted to moles. Now we need to apply our mole to mole ratio. So bringing NaCl down so it cancels, putting moles of copper 2 nitrate, our goal, on the top. We now need to know the numbers that fill in these blanks, the stoichiometric ratio. So if we go to the balanced equation and look at NaCl, we see that there's a 2 in front. When we go to copper 2 nitrate, we see that there's nothing in front, meaning that's an understood 1. Now moving on from there, we go 1 mole of CuNO3 2, running a little tight on space. And now we need to figure out the mass of copper 2 nitrate. So looking up copper, we find out that it is 63.5. We know that nitrogen, looking up nitrogen, nitrogen's mass is 14, but you'll notice that there's 2 of them, so that would make the total mass of nitrogen 28.0, and then oxygen, you may even remember, is 16, but you'll notice that there are 6 of them for a total of 96 grams. Now adding these numbers together, 96 plus 28 plus 63.5, and I get 187.5 grams of CuNO3 2. Now we're ready to do the math. And you'll remember that we multiply by the top and divide by the bottom. So we have 10.2 divided by 58.5 divided by 2 times 187.5. And being limited then to 3 significant digits, the answer is 16.3 grams. So what we just found out is that if we react 10.2 grams of NaCl, it will take 16.3 grams of copper 2 nitrate to react with it. Now, the important thing probably for you to remember at this point is that every mass problem that you have done or ever will do in this class, they all work like this. You will always start with a mass, you will always solve for a mass, and it will always be 3 steps: converting grams to moles for your starting point, then the mole to mole ratio, and then converting moles to grams for your goal. Those are always the steps to these problems. Now we're ready to take this idea of mass problems, and we're ready to incorporate it into a bigger process called percent yield. Percent yield is actually the way for us to represent how well we did when we carry out a chemical reaction. Chemical reactions produce products, and as a chemist, what we want to do is we want to collect as much product as we possibly can. Now, in order to figure out how well we did, we talk about a ratio called percent yield. And percent yield is actually a ratio of how much we actually collected, that's from experimentation, and then how much we theoretically could have produced, and that actually comes as the result of a mass-mass problem. Now, in order to solve these problems, we actually take a mass-mass problem and make it a part of a bigger process. So the first thing, of course, we need to do is write a balanced equation. Once we have the balanced equation written, we will always start with the mass of a reactant. Then we will set our goal at the mass of what we call the known product, the product that we know how much we produced. Then we'll solve the mass-mass problem, just like we did on the previous slide, and then finally we'll take the result of that mass-mass problem and use it as the theoretical yield in our percent yield equation. So taking a shot at this then, here's an example problem. We've got 15.5 grams of methane. You may remember that's Bunsen burner gas, the stuff that comes out of our gas taps in lab. And we're going to combust this with excess oxygen. And remember that excess means all that we need and more. And when we do that, we collect 32.1 grams of water. The question is, what's our percent yield? So the first thing that we need is a balanced equation. It balances with the 2 in front of the oxygen and in front of the water. So then what we want to do is gather together our information. And we know from the problem that we're starting with 15.5 grams of CH4. Now we know that we collected 32.1 grams of water, so we're going to write that down as well. So now we have a sense of what we're figuring out. We know that we're starting with 15.5 grams of CH4. We've got all the oxygen that we need to make all of that CH4 react. And at the end of that, we collect 32.1 grams of water. The question is, how did we do? Is 32.1 grams of water all the water that we could have collected from burning 15.5 grams of CH4? Or did we lose a lot? Well, in order to find out, what we need to do is we need to calculate how much water we could make from 15.5 grams of CH4. So we set up a dimensional analysis grid, and you'll notice that the 15.5 grams of CH4 becomes our starting point. We always start with the mass of a reactant. Then, off to the right, we will set our goal at the mass of our known product. And the product that we know the mass of is the water, so that will be our goal. Now we need to do the dimensional analysis. And again, this is a mass-mass problem just like the one we solved a second ago. First thing we do is convert grams to moles. Carbon is 12, hydrogen is 1, and there's 4 of them. We add that up and it's 16 grams per mole. Then we need the mole to mole ratio. So you'll notice that we've got moles of our starting point on the bottom, and we've got moles of our goal on top. So we need to find the numbers that are in front. So if we look at the CH4, we notice that there's no number in front of the CH4, so that's an understood 1. And then if we look at the O2, we see that there's a 2 there, and that would be the stoichiometric ratio. Then the last thing that we need to do is convert moles to grams, where oxygen is 16 and hydrogen is 1 times 2, which is 18. And then we do the math. So it's 15.5 divided by 16 times 2 times 18, and our answer is 34.9 grams. So what that means then is this. If we start with 15.5 grams of CH4, and if we react it with all the oxygen that we need, we now know that we should be able to make 34.9 grams of water. Now we got a problem. We only collected 32.1 grams of water. We lost some. But it's not enough to just say that we lost some. We actually don't talk about how much we lost. We talk about how much we collected. And it's not enough to just say most. We want to represent it with a number. That is where our percent yield comes into play. And as we calculate percent yield, the top number is our actual amount. How much water did we actually make? And you'll notice that this number is actually given to us in the question. It is 32.1 grams. Then we need to know how much water we theoretically could have made, and that number comes as the result of the mass-mass problem. and then we do the math and we find out that this is 92%. So now we've understood how to do mass problems, and more specifically how to do percent yield problems. But now we need to talk about how this all comes together on the sample question that you had off of the lab. And in the lab question, the difference is this. You were not given how much reactant you started with. You may remember that in the lab, the reactant that we started with was NaHCO3. And you had to calculate how much NaHCO3 you started with. You weren't given this number, but you had to find it by subtracting masses, mass by difference, just like we talked about a second ago. And that will be true on the homework and the remediation work as well. You'll be solving a percent yield problem, but it'll be like the work in the lab. And again, you will be figuring out how much sodium bicarbonate you started with by doing mass subtraction. Then the other number that's important in this process is your actual yield. In the lab, it was NaCl. The product that we isolated was NaCl. But again, you were not told how much NaCl you isolated. You actually weighed the dish, and then you weighed the dish with the product, which was the salt, and then you found that again by subtraction. So the connection then is that while the problem that you'll be held accountable for, which is more of a lab type setting, does follow this pattern, the difference is that we're expecting you to be able to find the mass of your reactant and the mass of your known product by doing subtractions. And again, representing those subtractions the way that we just shared, which is how we've been doing this all year. So that's the end of this remediation video. Your next step is to, if you haven't already, print the remediation assignment that is posted on our website and complete it. There's the opportunity for you to balance some equations, and then you'll notice on the back there's the opportunity for you to revisit the percent yield lab, pulling together everything that you just reviewed. Then what you'll do is you will gather together the notes from this video and that remediation assignment, and remember to check your answers. The answers are posted to the remediation assignment. Check that on our website, make sure you're doing them right, ask questions if you're not, and you will come to a Pride remediation session. These will either be Tuesday, March 21st or Wednesday, March 22nd. They will be in Mr. Knappenberger's room. In order to get in, you need to be there before noon, 12 o'clock. You need to have your video notes, and you need to have the remediation video homework assignment done. During this Pride session, you'll receive additional instruction, and you'll receive an additional homework assignment. This additional homework assignment then becomes your ticket into the replacement test. The answers for the Pride assignment are also posted on our website. So you will then take that assignment home, you'll work on it, complete it, check your answers. Again, if you have questions, make sure that you're getting them addressed. And that assignment then becomes your ticket into the replacement test. The replacement test will be Thursday, March 23rd during Pride. It will be with your teacher. So it will not just be with Mr. Knappenberger. Ms. Call's students will be with her. Again, the test starts at noon. And in order to get into the test, you need to bring with you the homework assignment that you received during Pride. Then again, as I think you know, if you get better than 80% on the replacement test, regardless of what you got on the test the first time, we will replace that score with a 75%. So thank you for watching the video. Good luck with your remediation and restudy. Please get with your teachers or other resources if you need additional support, and we look forward to seeing you at Pride.